All right. So, welcome to the to today's seminar. Okay. So before starting today's seminar, I would like to ask a question first. Okay, something for you to think about. Okay. So, what have we proved so far? We know if lambda is the doubling dimension. Okay, of the metric space. Okay, so the metric space includes a ground set as well as a distance function. Okay, and then disk ANN says, there is a data structure with how much space. So this is the number of edges, and therefore this is also the space. Just to remind you, n is the number of points in the data set, and epsilon is 1 plus epsilon, right? So this approximation ratio there, and delta, so that is the aspect ratio of your data set, okay? So this is the space, and query is 1 over epsilon to the power of lambda, and then log squared. Okay, so that's query. Okay, good. So I already said that, if you want to have a plausible explanation about the performance of disk ANN in practice, this lambda will have to be small, okay? Otherwise, very quickly, this exponential term can kill you, correct? Okay. Now let's think about a typical application of disk ANN in practice. Okay, so what they do is say they use some sort of embedding models, if you understand what I'm saying. Okay, for example, if you have say a document, okay, and then you can map the document into a multidimensional space. Okay, so typically, for example, if you use BERT, okay, and then you will be converting a document like a paper into, say, a 500 plus dimensions. Okay, so in other words, if you look at it, this P is going to be a set of 500, let's say 512. I would like to say 512, but I'm not very sure about that. Let's say a set of 500 plus dimensional points. Okay. And if I have a query, so this query, say that's also a document, right? So this document will also be embedded into the same dimensional space. Okay. So everything's very high dimensional if you look at it. Okay. So I already told you there is a relationship between doubling dimension and Euclidean dimensionality, correct? So in general, if you have, let's say, a d-dimensional space, Euclidean space, right? And if you want to look at its doubling dimension, then you can prove this relationship. So lambda, okay, so doubling dimension is at least d. See what I'm saying? Okay. Now here is the question. Here is the question. Okay, why is this a plausible explanation? See what I mean? Okay, so let me ask you this question once again. You can see that the dimensionality is really, really high. Okay. Now, I told you before, right? If the data space is d-dimensional space, Euclidean space, then the doubling dimension satisfies this inequality. It's at least d. That's the bad news, right? But the good news is big O of d, right? But the bad news is very bad already. You see what I'm saying? Okay. So if this lambda is 500 and let's say 500, right? So this 1 over epsilon, even if epsilon is just a half, let's say, and then 2 to the power of lambda, that's a huge thing, right? So why is this a plausible explanation? Okay. Well, I would say this is a thought-provoking question. All right, so I'm not going to answer that question. So that's a very, very good thing for a discussion. Okay, all right. Moving on. Okay. So today we will talk about another mathematical tool. Okay. In general, if you want to reason with metric spaces from theoretical computer science, there's something called RNets. Okay, epsilon net, very similar name, but completely different meanings. Okay, RNets. Okay, and so this RNet is a very, very elegant machinery that has been used to solve many, many problems in metric spaces, including approximate nearest neighbor search. Okay. And so far, if you have attended all the seminars, and then you would know we have never mentioned this RNet before. Okay. Indeed, if you look at the literature of proximity graphs, I would say it's quite a surprise that this notion of RNet was rarely mentioned in the literature. Okay, so I don't know why that is the case. So today we will look at this RNet. Okay, so I will do not too shallow. I would do a not too shallow introduction to RNets, and then I'm going to show you another way to build a proximity graph that achieves the same space and query complexities of disk ANN. Okay, another way completely different. In fact, this new way, this new approach for building this proximity graph has an advantage over disk ANN. So if you look at disk ANN, the space complexity and query complexity are pretty good, right? But there's one thing with disk ANN, its construction is very slow. Okay, so currently, all the known algorithms for building the disk ANN, all of them are very slow. In fact, the fastest algorithm today runs in n cube time. Okay, n is the number of points once again. Okay, I thought about this myself. I think I should be able to reduce the cubic time complexity to n squared. But even n squared is something very, very large. Okay, and today I would say people do not have any algorithm that can do better than n squared. Okay, actually, I don't think there have been any published algorithms faster than n cube. Okay, so this is an issue. Okay, on the other hand, by virtue of the rich literature that people have already built on RNet, you will see that this new proximity graph can be constructed much faster. Okay, so basically n polylog time. Okay, so we will see about that later. Okay. So once again, I would like to emphasize that today's talk is mainly about RNet. Okay, so I think it would be remiss of me not to talk about RNet. Okay, no, you have learned a lot of things about proximity graphs that might give you this illusion that everything will have to be about proximity graphs. Okay, so today's talk aims to correct that illusion because it's not true. Okay, actually, quite to the contrary, I would say it is the RNet that plays a more important role in the history of theoretical computer science on metric spaces. Okay. Now, let's talk about RNet. Okay, so first of all, the usual stuff. All right, so we've got a metric space. So you already know what that is. And we have a lambda. We use lambda to represent the doubling dimension. And this lambda is a constant. Okay, so all our discussion will be under will be carried out in the regime where this lambda is a constant. Okay, so in theoretical computer science, this is referred to as the low dimensional space. Okay, low dimensional space. Okay, in the previous lecture, we somehow justify this assumption, right? Because if lambda is unboundedly large, and then there's nothing you can do to outperform brute force scan. Okay, so today all our discussion will be carried out under this assumption. What else? And we have a set of points. Okay, so this is a set of points, same as before. N is the size, and also delta, so that is the aspect ratio. Okay, aspect ratio. All right, good. Very nice. Now here, I would like to define RNet. Okay. So RNet, you first of all, you have to specify a value of R. So this is a real value. Okay, so this real value, let's say, is larger than or equal to 0. Okay, and this RNet is a set. Okay, and RNet is a subset. Call it Y. Okay, this subset. This is a subset of P. Okay, in other words, you want to identify certain good points from the data set. Okay, and call the collection of these points an RNet. Of course, many subsets, right? So we need to have some requirements. So there are two requirements. The first one is the separation requirement, separation property. So this separation property says if you pick 2 points into this Y, okay, I will refer to those points as centers for reasons that will be clear later. Okay, so let's say you pick a subset. Okay, so these points in the subset, they are referred to as centers. Now these centers will have to be quite far from each other. Okay, so for any 2 centers in the RNet, you must have this condition satisfied. Okay, so the distance between R1 and R2, they will have to be at least R. Okay, so no 2 centers can be too close. Okay, well, later on, when I talk about how to construct this set, it will be very instructive to think about these centers as McDonald's. Okay, so it's going to be a very good analogy, as you will see. Okay, so imagine you want to pick locations to build McDonald's. Okay, you don't want to have 2 McDonald's that are just next to each other. It doesn't make any sense. Okay, so this is the separation property. But there's another property that is very important. This is called the covering property. Okay, the covering property basically says that, you know, for any point in the set P, okay, in the original P, there gotta be a center that is close to it. Okay, that is close to it. Again, the McDonald example is a very good example here. So you can imagine P as the set of interesting locations in Singapore, and you would like to build McDonald's to make sure that every location in Singapore is close to some McDonald. Okay, now formally, this says for any P in the data set, okay, there exists at least one center or McDonald, okay, such that the distance between this point and the center is bounded by R. Okay, so if this is the case, and then you have an R net. Okay, why net? Well, let's not dwell on that name. There are some legacy reasons why it's called a net. Okay, in fact, it will be clearer in the next lecture when we talk about navigating net. All right, but ignore this name for this for the time being. That's an RNet. Okay, that's an RNet. Well, let's have some example, shall we? Now, let's say if R is 0, if R is 0, and then you can see there's only one RNet possible. All right, there's only one RNet possible because you have n points. Say I'm a point, okay? And if you think about it, I would include myself into this 0 net, okay? And every point is included into the 0 net. So the 0 net is just P itself, okay? So let's see if it satisfies the 2 requirements, right? So any 2 points, their distance will have to be greater than 0, which is true because that's the definition of the metric space. Okay, and furthermore, trivially, we get everybody covered because everybody is included into the RNet, right? Okay, so now let's consider another extreme example where R is, say, infinity. Okay, R is infinity. And then in this case, your RNet can consist of only 1 point. Okay, only 1 point, right? Because 1 point will be sufficient to satisfy the covering property. Okay, however, you cannot include another point because if you have 2 points, and then you will be violating the separation property. Okay, so now these two extreme examples basically illustrate, that RNet is something that can go from the entire data set to just one single point. Okay, so depending on the value of R, the smallest RNet could have any size from 1 to n. Okay. Well, as I said, there is a very, very rich literature on RNets. Okay, RNet is something very useful, and today we will see how this RNet can give us another proximity graph. Okay, that's very simple proximity graph that retains the space and query complexities of disk A and M. Okay. A very important reason why people like RNet so much is that, this RNet can be computed efficiently. Okay, so now this is something very important. Okay, so if you think about this shortcut property guaranteed by disk A and N, that's a very nice property. However, the thing is, if you want to compute the out edges, to satisfy the shortcut property, it's not easy. That's precisely the challenge, preventing people from designing a fast algorithm for disk A and N. Okay. However, RNet, because RNet is something that people have done a lot of investigation, now we can just, take a free ride. Okay, we can stand on the shoulder of a giant. That's what I mean. So you can take it for granted that the next result is true. Okay, so for any R, an RNet can be computed, can be found in how much time, and log and delta. Okay. By the way, this log and delta is just log n plus log delta. You see what I mean? Okay. So typically in practice, delta would not be something like 2 to the power of n. Okay. If it is, and then this complexity is large. But if delta, let's say it's a polynomial of n, okay, and then this is going to be just n log n. All right. So this algorithm is not a trivial algorithm. Okay, so today I will not tell you completely how this algorithm runs, but I will give you a rough idea. Okay, so if you want to compute an RNet, there is one famous greedy algorithm user. Okay, so first of all, you pick an arbitrary point in the data set, and this is the first center you would like to pick. Okay, the first center. Now think about this is the first McDonald. Okay, first McDonald. Now I'm going to define McDonald distance for every other point. Okay, so in general, McDonald distance of a point is how much this point will have to move to get to the nearest McDonald. You see what I mean? Okay, all right. Now if I say what is the McDonald distance of this point, well, the answer is 0. Okay, the answer is 0. All right. What is the McDonald distance of another point? Is just a straight line distance in this case. Okay, but remember this is a metric space, so you don't really have straight line distance. Okay. Now you can remove all those points whose McDonald distances are already larger than or smaller than or equal to R, because those points have already been covered by this center. Okay, so you do some pruning. Okay. All right. Now if the data set is already empty, then you are done. Right? So this is the only center. Okay. Otherwise, you look for the point with the largest McDonald distance. Okay, largest McDonald distance. All right. So in plain words, this is essentially the most unhappy guy in the data set because if you choose to build a center here, and then this guy would have to walk the longest distance in order to eat McDonald's. You see what I mean? Okay, so you make this guy, you turn this guy into the happiest guy, okay, from the most unhappy to the happiest guy. All right, so this is the second center there. All right, so if you do that, again, you can do the pruning. You see what I mean? So because this guy, this new center might get some other locations covered, right? So the covering property here, right? Remove all those points, okay? Remove all those points, all right? And then repeat the trick, okay? Repeat this step among the remaining customers' points, okay? Find the point whose current McDonald distance is the largest, okay? But pay attention here, right? Because I have got two centers here. What's the definition of McDonald distance? Well, this is, if I have a point P, okay, so this will have to be the smaller of the two distances here, because you can choose, you can go to either McDonald, and by definition, you have to go to the nearest McDonald. You see what I mean? So the McDonald distance is defined as, you know, how much you have to walk in order to get to the nearest McDonald. Okay, so every point, identity point, has a McDonald distance. Okay, so you want to identify the point with the greatest McDonald distance, and then that's where the next center is. Okay, and again, you can do this pruning after you have introduced another center. Is that correct? So you keep doing it until all the points, until the data set becomes empty. Okay, so if you implement this algorithm in a naive manner, this is n times k, where k is the number of points in the center. Okay, however, you can do much better than this, because you don't really have to be so naive. You know, every time I pick a new center, then I have to scan all the remaining points. You know, there are data structures you can build, you know, based on those distances, McDonald distances. That's what I meant. And then, you know, at each iteration, you know, you are able to identify the next center very quickly, and then you are able to update the data structure. So that's sort of the ideas, okay? But there are details, all right? So to cut a very long story short, you can take it for granted that, you know, an RNet can be built in so much time, okay? So this n log n delta, okay, good. Now, before I continue to talk about proximity graphs, let's talk about packing lemma, because that's one very important reason why you want to use an RNet, okay? So for that purpose, I have to go back to this aspect ratio lemma, which has been included into the lecture notes, I think the second seminar, but I never got a chance to talk about it, okay? Now today, this lemma is going to play a very important role. So let's recall what the aspect ratio lemma is saying. Okay, so let's say you have got a set. Now this set can be any subset, just like P, right? Can be any subset of the metric space. Okay, so let's say if we know the aspect ratio of X is A. Okay, so in the metric space, you're able to prove that, you know, this X can be represented using A. That's quite interesting. Okay, it can be represented using A. So this is bounded by A times A to the power of lambda. Okay, by the way, as I said, today we assume lambda to be a constant, right? So if that is the case, A to the power of a constant, that's just a constant, okay? So you can write this into A to the power of lambda. Okay, so this is the aspect ratio lemma. Okay, aspect ratio. All right. So today I will not prove this lemma, but the whole proof has been included in the, I think, the second seminar's lecture notes. It's not difficult. Okay, so there in that lecture notes, in those lecture notes, I talked about a covering lemma, and then, you know, look at that covering lemma, and then this aspect ratio lemma is a corollary of that covering lemma. Okay, but this lemma is very easy to remember, right? So basically, you just have to look at the aspect ratio. Okay, so aspect ratio A. Oh, by the way, what's the aspect ratio of a set? Maximum interpoint distance divided by the minimum interpoint distance. Okay, so that is the aspect ratio. So it says the size of this set cannot be more than a to the power of lambda. Okay, so that is the aspect ratio. Good. Well, we will utilize this aspect ratio to talk about another very important lemma, okay, except that with the aspect ratio, that lemma becomes a corollary, okay? So this is the famous packing lemma, okay? But this corollary, the corollary can be stated as follows, okay? So corollary, all right? Now let's say Y is an R-net of P. Now, don't forget, if you want to build an R-net, you have to give me the value of R first. Okay, so now I have an R-net. Now, this R is very important. Now, watch carefully. So I look at this R, and then I say, okay, I take a ball of radius, say phi times R, phi times R. Okay, so this is relative to R. Okay, so larger than R by a factor of phi, and phi here is something at least 1, let's say. Okay, good. So still remember how a ball is defined, right? A ball is a set. You see what I'm saying? In here, I do not even bother to mention the center of the ball because, you can give me any ball, all right? But in general, if you want to specify the ball, you give me a center, give me a radius, and then I can include all the objects, all the points in the metric space whose distances to the center are less than or equal to R, correct? Okay, so this ball is a set, okay? And Y is also a set. You see what I'm saying? Y, so 2 sets. Now I can talk about the intersection of these 2 sets. Okay. Basically, this is saying you take an R-net, and now I have got a ball. So you have R-net inside, right? And how many points there can be in this ball? You see what I'm saying? In this R-net, right? So the answer is, this is no more than phi to the power of lambda, okay, up to some constant, okay? So why this is called the packing lemma? Because I'm sure you have been asked questions of the following type, right? So let's say you have a ball, okay, with some radius, and then you have some small balls, okay, small balls. So these small balls, they have some smaller radius, but all the small balls have the same radius, okay? So now you want to prove, okay, there cannot be too many small balls that you can pack into the big ball, right? So this is the sort of questions that come up again and again. You see what I'm saying? Except that sometimes we talk about cubes, we talk about balls, and in general, you can talk about balls in any LT norm. Okay, you see what I'm saying? All right. Now, all of them can be captured by this corollary. Okay, all of them, because this is the power of metric spaces, right? I don't really care what is the distance metric. Okay, so as long as you know the phi, all right. So the phi. Okay, so this is, and then immediately you can calculate it like this. Okay, so for example, if you are talking about any constant dimensional space. Okay, let's say 10-dimensional space, 2-dimensional space, 20-dimensional space, doesn't matter. If I ask you, okay, now I've got a big ball of 10R, okay, 10R, R some value, right? And then I say, how many small balls of radius R? Okay, you can insert into the big ball, right? And the answer is a constant. That's what I'm saying. All right, the answer is a constant because now the phi is like 10, right? And I talked about a constant dimensionality, so it's a constant. All right, so that is the power of this packing lemma. Okay, so this thing is very, very handy. Okay, so typically, whenever people use RNet, they will have to use something like this. Okay, good. Nice. So that's the background. Okay, so this RNet, now we have this tool. So, so the next question is, how can we build a proximity graph using this tool. Okay. In retro, so I'm going to introduce a graph, and then later on, I'm going to explain to you why this is a proximity graph and why its current time is good, right? But there's one remark I would like to make here. In retrospect, as I said, it's very surprising that this RNet concept was rarely mentioned in the literature. Okay, so today you will see there are natural connections between this very classical concept and this modern notion of proximity graphs. Okay, so in retrospect, the connections seem to be very, very natural. Okay, so I'm going to describe how to build a proximity graph. Okay, now, we've got this P. All right, we've got this P, and just for convenience, let's say the smallest interpoint distance of P is 2. Okay. Well, I don't lose any generality here because you can always scale up and down the distance function, right? So just to make sure that the minimum distance is 2, right? Okay. So I have this delta, right? So delta is d max over d min, right? So d max, by the way, is just the diameter. This is just the diameter. Okay, let's write it properly. So diameter of P. All right, so that is the definition of diameter. Okay, what is the largest interpoint distance of P? Okay, all right. So we have this relationship, right? In other words, the diameter of P is just 2 delta. Okay. All right, so I'm going to introduce this H. Okay, so this H, not surprising at all. This is something that you will be expecting, right? So this is basically log delta. Okay, good. Now, this H is an integer, as you can see, right? The ceiling. So, I look at every integer I from 0 to H. Okay, all right. So there are H plus 1 different values of I. And don't forget, H is at the order of log delta, okay? So what are we going to do? Well, we look at the distance 2 to the power of I. You see what I mean? Okay. So essentially, if you think about it, the distance from 0 to diameter, okay, 2 delta, right? So now, basically, we have cut it into intervals, right? So from 0 to 2 to the power of 1, but not including 2 to the power of 1, okay? And then 2 to the power of 1 to 2 to the power of 2, etc., right? I think we saw a similar trick before when we proved something about this ANN before. But anyway, so far, it's fairly simple, right? Simply says, okay, you look at 2 to the power of 0, you look at 2 to the power of 1, you look at 2 to the power of 2, etc., right? So you look at these H plus 1 different values of R, okay? Now for every R, what do? Build an RNet. Okay, so let's say yi is n, okay, let's say a 2 to the power of I net, okay? So you build this net, okay? So this can be done efficiently because every net can be constructed efficiently. All good? Okay, nice. All right, so you have the net there, okay? You have log delta nets there, and then I'm going to create the out edges for every point, okay? And then I have a graph, okay? And later I'm going to show you that this is a good graph, okay? All right, so for this purpose, I'm going to introduce some handy notations, okay? So this eta, this is defined as this, okay? At this point, don't ask me why this is 1 plus 2 over epsilon. You know, there's always some weird looking constants when you talk about theoretical stuff, right? Well, the only thing I want you to note is that this eta is at the order of log of 1 over epsilon, and that's it. Okay, so 1 over epsilon, and then take the log, that's basically eta, okay? And then I'm going to talk about this phi. I will also need this phi. I also need this phi. So this phi is defined as 1 plus 2 to the power of eta plus 1. Okay. Again, don't ask me why this is eta plus 1 and why this is 1 plus. All right. So the design is due to the proofs later. Okay. And once again, it would be useful to understand the order. Okay. So I already told you before this eta, this is at the order of log of 1 over epsilon. Okay. And this b is at the order of 1 over epsilon. So here I emphasize this is a big theta. So basically this is 1 over epsilon. Okay. So you can just imagine that this eta is log of phi, and that's basically correct. Okay. And this phi is just 1 over epsilon. So that's very easy to remember. Okay. Okay, good. Now, nice. Okay, so here I'm going to build the graph, just one single sentence. Okay, so for every point, okay, for every point P, okay, so you do the following. For every I, from 0 to H, basically, I want you to look at every R net that you have built, okay, Yi, okay? So from Yi, you want to pick some points to connect to. Okay, so that's the idea. Okay, create an edge. From P to Y, small y. Okay, and so this for each, let's write it this way, for each small y in the net, such that the distance of P to that small y is bounded by phi times 2 to the power of I. Okay. All right, so let's take another look at the construction. Okay, so what are we doing? First of all, you see you are looking at a point P. Okay, so in the beginning you don't have out edges. Now I'm going to construct out edges. Okay, now you have nets, right? You have 2 to the power of 0 net. You have 2 to the power of 1 net. 2 to the power of H net. You have H of them. Okay, so now let's say you look at this I. For any I from 0 to H, right? So I want you to look at Yi. Now, don't forget, Yi is a 2 to the power of I net, right? So what's the meaning of 2 to the power of I net? You see two centers in that net, right? They will have to be 2 to the power of I distance apart, right? And each one of them, they will have to cover the points, with the vicinity. And the radius of the vicinity is 2 to the power of I, okay? All right? So you see, it's very important to look at this 2 to the power of I. Okay, so because this 2 to the power of I determines everything, right? Determines the covering, determines the separation, correct? Okay, good. Now you see, essentially what I'm saying is, now look at this point. You look at those McDonald's, okay? You look at those McDonald's, and those McDonald's, they are at least 2 to the power of I apart, okay? Now you look at all those McDonald's, and you want to connect you to some candidate McDonald's, okay, close McDonald's, all right? Now, what do I mean by close? Close says this is roughly 1 over epsilon times this, again, this very important value of R that is deciding everything. You see what I'm saying? Okay, so for example, here, if phi is 10, then basically saying, if this McDonald is within distance 10 times R, and then I would remember it, and then I will create an out edge from me to that McDonald. Okay, so this is what is happening. Okay, so to give you another illustration, now think about covering. So this is a McDonald. All right, so this McDonald guarantees, there's a vicinity, and this vicinity covers some points, right? So if you build more McDonald's, and then all these circles together will cover all the points in the data set. Okay. Now, conversely, if you look at the data set, if you look at a point P, okay, and you want to overkill. You see what I'm saying? You want to overkill. So you want to look at a larger vicinity, and this vicinity is phi times this R. You see what I'm saying? Okay, and then you look at all the McDonald's that are within this vicinity. And what you want to do is you want to create out edges to every other McDonald's. Oops, sorry. So this is an illustration. Okay, so it's very important to have some overshooting here. Okay, so not just R, but let's say phi times R. Okay, phi could be 9, could be 10, could be something large. Okay, all right. So this is the graph. Okay, so this is the graph. So this graph can be constructed efficiently. Okay, I would not go into the details today. Okay, good. Is this too heavy? Do you understand? Do you want to ask any questions at this point? Okay, how the graph is constructed? Okay, so RNet. Okay, all right. So you do this, and then you put together all the out edges. Okay, all right. It's possible, you know, the same McDonald gets connected twice, but only one edge is retained, of course. Good. All right, so if this is clear to you, and then next we will talk about why this is a good thing to have, okay? So in the lecture notes, I give a proof. You can prove that if this is what you do, then every point has at least one out edge, okay? One out edge, okay? So today in the seminar, I will just take it for granted, okay? I will not go into the proof. The proof is not difficult, all right? Okay, so why do I need this? Okay, I need this because later on, I will be able to say something like, you give me a query, and then I look at my best out neighbor. You see what I'm saying? Okay, because if I didn't have the fact that, you know, there must be an out neighbor, then I don't really get the right to say, look at my best out neighbor, right? So that's why I would like to insert a remark here. Okay, good. Now, let's analyze how many edges you can have for every single point, okay? How many edges you can have for every single point, okay? So this is the out degree bound for each point. So if I can bound the out degree, and then I can bound the total number of edges. Okay, good. In fact, this is fairly easy because we are standing on the shoulder of a giant, right? So you already know this corollary here. As you can see, let's take another look, right? So it says if you have an RNet, okay, you place any ball there, okay? It's just that the ball will have to have a radius that is relative to R, right? So it's phi times R, okay? So if I ask you how many points there can be in the ball, I mean, from the centers, right? How many centers can there be in the ball? The answer is, well, you know, just phi to the power of lambda, right? Good. Well, if that is the case, you look at what's happening here. I think this illustration is a very capable illustration, right? So look, I'm looking at this phi times R from myself, right? So I am this point P here, right? So basically, I'm considering only the centers, okay? Only the centers. So these red points, they are the centers in this 2 to the power of I net, right? So R is 2 to the power of I here, okay? So I look at this ball, and you have an R net here, and the value of R is 2 to the power of I, okay? So if I ask you how many red centers there can be, well, the answer is phi to the power of lambda, okay? Phi to the power of lambda, right? So this is immediate. This can be obtained immediately from the corollary that I talked about, okay? Well, this is not precisely the out degree because remember, we have to do this for each layer. You see what I'm saying? Okay, so this value of I increases from 0 all the way to h, right? So for every I, you can prove by resorting to this RNet result, right? You can prove phi to the power of lambda. So that will be an upper bound, and you have to multiply that by h, right? So h is at the order of log delta, okay? And therefore, immediately, you can see that the out degree is bounded by this. Now, don't forget this phi, right? I told you before, whenever you see phi, you just think about it as 1 over epsilon, okay? So this is bounded by 1 over epsilon, the power of lambda, and then log delta. Okay, so this is reconstructing the result of disk ANN. Okay, good. All right, so as I said, this graph can be constructed efficiently. Now, what do I mean by that? So the construction algorithm, the fastest construction algorithm is this. Okay, 1 over epsilon to the power of lambda times m, and then polylog. Okay, so this is the construction time. Okay, so I want to add a remark that this construction time can no longer be improved significantly. Why? Because you will be writing down at least so many edges. Okay, so this is the number of edges. Okay, and by the way, so last time we proved the lower bound on the log delta, right? Something I did not tell you is that there is another lower bound showing that so many edges are compulsory. Okay, 1 over epsilon to the power of lambda. In other words, this term is necessary. Okay, but the argument is more complex. Okay, so we didn't talk about that. But just so you know, this term is absolutely necessary. 1 over epsilon to the power of lambda times n. Okay, and since you will be writing down so many edges at least, this polylog basically is the only thing you can improve on. Okay, so whatever you do will be improving on the polylog. All right. I think today's material is a little deep, right? So it's getting more and more difficult. Okay. All right, good. Now, next, I'm going to show you why. So next, I'm going to explain why this is a good graph to have. Okay, so for that purpose, I will have to show you two things. Okay, first, this is a 1 plus epsilon PG. Okay, 1 plus epsilon PG. Okay, and the next thing is, the query time is good. Okay, the query time is the same as disk ANN. Okay, turns out that both results are non-trivial. Okay, both results are non-trivial. And I will not talk about the first result. Okay, so the first result, once again, says that this is a 1 plus epsilon PG. Okay, this is not a trivial proof, but this is not very interesting. So I will skip on that. Okay, I have a reference there. You can read the reference if you want. However, what is much more important is the second lemma. The second lemma says, the query time is small. Actually, this small query time is a corollary of another very important lemma. This is known as the log drop property. Now, this log drop property is super important. Okay, so this warrants a discussion on its own. So this is what I'm going to focus on next. Okay. So I will first describe what is this log drop property. Okay, so I'm going to state the property in full, and then I will analyze it. Okay, I will try to prove at least a part of it. Okay. So what I will be presenting is a simplified version of the full log drop property. It's a special version, but it suffices for our purpose today. Okay, so let's call it lemma. Now you think about any query in the matrix space, any query in the matrix space, and you think about any vertex in the data set. Okay, so I add a little circle here, P circle, to emphasize, this is a vertex we are focusing on. Okay, so you can imagine what happens when the greedy algorithm is standing at this hop vertex. So this P circle is the vertex that greedy is standing at. Okay. All right, good. Now, here is something I can define, because I showed you, I mentioned to you before that every vertex has an out degree at least 1. Okay, so that allows me to define something like this. So this is the best out neighbor of this P circle for Q. All right, so this is the best out neighbor. All right, so once again, imagine greedy algorithm. The greedy algorithm is standing at P circle, right? So among all the out neighbors, which one greedy algorithm is going to go for, right? So this is P plus out, okay? P plus out, all right? So I will also need this P star. This is an exact nearest neighbor of Q. I said an exact instead of the exact because it's possible you could have multiple exact nearest neighbors, right? Anyone will do. So this is P star, okay? Now, the log drop property says this, okay? So if P plus L is not a 1 plus epsilon ANN of Q, okay? All right, then something nice happens, okay? So let me write down the math and then I will explain, okay? Okay, so let me explain. Now, if you look at the inequality here, right? Now pay attention. So here, this is a log, all right? Log of this distance from the out neighbor to P star. P star is sort of like the destination, right? All right, now take the log, but you also have the ceiling. You see what I mean? So now basically you have an integer here, okay? Now on the right-hand side, it's similar, except that here, this is about the distance where this, the distance from where you are currently at P circle to the destination. You see what I mean? Okay. Now I want you to think about this like the following. Look at the distance domain, right? The distance domain. So the distance domain, you can think about it as, you know, like fractional, right? So goes from 0 and then from 0 to 1, so that would be sort of like the first interval. And then from 1 to 2, so that would be the second interval. And then from 2 to 4, that would be the next interval, and so on and so forth. You see what I'm saying? Okay. So there are so many. So you can divide the distance domain into exponentially increasing intervals like this. Okay. And then basically this is saying these two guys, after taking the, so these guys, right? These guys, when I say guys, I mean the distance, the distances themselves, right? They will have to fall into different, you see what I mean? Different intervals, okay? Because if you are here, right? If you are here and then you, after taking the log, it's going to be 1 point something, right? So if you do the ceiling and then you get snapped to 2, you see what I'm saying? So similarly, if a distance falls into this interval and then you take the log, it's going to be 2 point something, right? So if you take the ceiling, it gets snapped to 3. You see what I'm saying? Okay. But now look at this inequality here. This is strict. All right, this is strict. So this essentially says if before your distance belongs to this interval, and then 1/2, your distance is going to belong to at least this interval, if not smaller. You see what I'm saying? Okay. So this is what the log drop property is talking about. Okay, log drop property. Okay. So this property immediately tells you that the query time is bounded. Okay, why? Because think about it, right? You start from the beginning. Okay, so your maximum distance is 2 delta. Still remember that's the diameter, right? 2 delta, right? So 2 delta is somewhere there, right? All right, so you make a hop. Now, if the next out neighbor is already good enough, it's already returnable. If this out neighbor is already a 1 plus epsilon, ANN, all good. Because we know that since this is a proximity graph, the greedy algorithm can only strictly improve the distance to the query point, right? So as long as you encounter one returnable point, and then all good. All right, so you will have an issue if you perform a hop and perform the hop again and again, and you never encounter any 1 plus epsilon nearest neighbor. So this is really a bad event, right? But the log drop property says, well, if this is the case, and then every time you will move to at least one interval to the left. You see what I'm saying? Okay, so in the beginning, you might be standing at the rightmost interval. So the rightmost interval has a number, right? So if this is 0, this is 1, this is 2, 3, and then it will be log delta, basically, right? And then after one bad event, if you don't see a 1 plus epsilon a and n, and then you must be moving from that interval maybe to the next one, okay, to the next to your left, if not smaller. You see what I'm saying? Okay, so every time you see a bad event, sort of like you are compensated by moving yourself from a far away interval to a closer interval to the origin, right? So you can only hop log delta times because there are log delta intervals here. You see what I'm saying? Okay. So after log delta hops, definitely, if you still haven't seen a good guy returnable, there must be a contradiction, because in the end, you come to the smallest interval, and the smallest interval, the distance is strictly less than 2. You see what I mean? It's from 0 to 1. So at that point, you must be standing at P star itself. You must have found the exact nearest neighbor. Okay. So this is the log drop property. Okay, the log drop property. Okay. All right. So I have used an hour. So officially, the seminar finishes here. So if you want to stay behind, I can show you the basic idea behind the proof. Okay, how the proof is done, and how this thing is connected to RNets. Okay.